cloud. There we go. Okay, recording. And then I think I have to do this. All right, so where do we want to start? Chapters 4, 5, 6? What do we want to do? 4? Okay, let's do 4. All right. All right, so the packet. Okay, so chapter 4 is kind of a continuation of stoichiometry, but in chapter 3, when we did stoichiometry, we were looking at like solids interacting, reacting with one another. We used BCA tables to calculate how much, reactant you need to make this much product. But there's other ways we can do chemical reactions, and you've already witnessed a lot of this in lab, is you can do chemical reactions in solution. So we need a better way to talk about how much substance is reacting, and that's us with the new concept of concentrations, where we can define a solution with a set amount of solute present given its molarity. And so it's directly related to, and I want you to relate concentrations to a way to figure out mole amounts of stuff reacting, like we did in chapter 3, where we used molar masses and gram amounts to figure out how much moles of junk we have. But molarity, concentration, is a new way to figure out how much junk we have given a volume with a certain concentration. That's the second half of chapter 4, where we get into solution stoichiometry, but then we also need to talk about some of the characteristics of dissolving stuff in solution. And so that comes into the idea of electrolytes. I actually just this weekend watched one of my favorite movies with the best Owen brother, and that's Luke. Wait, what's his name? Luke Olson. No. Okay, I'm having a brain fart right now. But anyway, my favorite movie is, you ever watch Idiocracy? It's an older movie. It was made in like 2004. Idiocracy? No one? No one? Or no one wants to say it. But in that movie, they talk about electrolytes, and they watered their plants with Gatorade, essentially, and it killed all their plants because they're just being stupid. And if anyone's listening and you watched Idiocracy, then I don't feel like an idiot talking about this. That movie is what I always think about when we talk about electrolytes, because it relates to how stuff dissolves in. Okay, perfect. Finally, yeah, someone is with it on me. You can watch it for free on YouTube. Yeah, you can watch it for free on YouTube. So electrolytes describe how stuff dissolves in solution. All right, we know, like, our intuition tells us that salt dissolves in water, sugar dissolves in water, but they behave differently in water. And so, when we drink a sports drink like Gatorade or Powerade or whatever, we say that these drinks possess electrolytes in them to replenish the salts that we sweat out of our bodies. And so those electrolytes are charged ions in solution. So those come from ionic salts dissolving in solution. So there are 3 different kinds of electrolytes. So let's just describe those. So we got strong, weak, and non-electrolytes. And so those relate to how they look in solution when you dissolve them. Strong electrolytes fully dissociate into their ions, where, like, if you put NaCl in solution, all right, and you dissolve it, you get out Na plus and Cl minus. That NaCl with both of those atoms connected to one another doesn't exist in solution. They actually exist as free cations and anions in solution. Non-electrolytes, on the other hand, don't form any ions in solution. So this would be like something like sugar, so no ions in solution. So if you just compare these 2 types of electrolytes, one will conduct electricity and then the other one will not, possesses no ions. All right, so we can go through all of these substances, and based upon their category, like what kind of substance is it? Is it ionic? Is it an acid? Is it molecular? We can figure out if it is what kind of electrolyte it is. So if we just go over the rules real quick, all right? So all the strong electrolytes are all ionic compounds. So this is kind of throwback to chapter 2. If you named it using ionic rules, right? you categorize that substance as ionic, and so then it makes it a strong electrolyte. So all ionic compounds, so any salt. And then other strong electrolytes include strong acids. All right, and that is something you need to memorize. There are 7 strong acids, so why don't we just go through them? There's 7 strong acids. What are they? What? HCl, yeah, so let's do the binary acids first. So HCl, what else? HBr, and then HI. See the kind of the trend here? Yeah, so we go down those halogens. It's all the halogens except HF, right? So those are 3 of them. What are some other? Are polyatomic acids. So nitric acid, so HNO3. Sulfuric, all right, H2SO4, and the chlorate ones, so HClO3 and HClO4 are all strong acids. So when you put these into solution, you will get free ions. That when you put HI in solution, you get H plus and HI floating around in solution. When nitric acid dissolves, you get H plus and nitrate on the other side over here. All right, so you break them up into ions in solution. All right, so those are our strong electrolytes. Non-electrolytes, so things that don't conduct electricity, are any molecular compound. Any molecular compound. So how do we know if something's molecular? When did we use molecular naming rules in chapter 2? We already tested you on this, by the way. It's when they were composed of all nonmetals. Those are our metals, all of our molecular compounds, all right? So therefore, let's just think about it. H2O, water. Water, what kind of compound is that? Based upon what I just wrote, molecular compounds are composed of all nonmetal elements, so that would make H2O what kind of compound? Ionic or molecular? Molecular, okay, so if it's molecular, if you put electrodes in pure water, distilled water, will it conduct electricity? No, it doesn't. So at least for my class, I showed the demonstration that pure water, like water, distilled water, like we paid money for it from the grocery store or from wherever, pure water does not conduct electricity because it's a molecular compound. It doesn't start conducting electricity until you dissolve salts in it, like any of these strong electrolytes. So you might think, we understand like water and electricity don't mix, right? You don't want to get like your electrical sockets wet. So the water that we interact with in the tap is not distilled water. It does have a little bit of stuff dissolved in it to make it conduct electricity. So do keep that in mind. All right, so I did strong, non, and then the weird one in the middle are any weak electrolytes, and those are our weak acids and bases. And so it's best to memorize those strong acids because anything that's not one of the 7 strong acids is automatically a weak acid, right? There's only one weak base that you need to memorize, and do we know what that is? Ammonia, NH3, all right? So those are our weak electrolytes. Okay, so those are the rules and how we identify stuff. And again, you like pull out those chapter 2 ideas. Do we separate acids into ions since they partially ionize, or do we not? So I should point this out, a weak acid. So a strong acid, when that dissolves into solution like HCl, we use this kind of arrow when it dissolves. So we get H plus and Cl minus dissolved in water. But when something like HF dissolves, is HF a strong acid? So then what kind of acid is it? Weak, yes, it has to be weak because it's not one of the 7 strong. I actually drew the wrong type of arrow. We want to use a double-sided arrow to show HF does partially ionize in solution, but there are some intact HF molecules present in there as well. So when you put HCl in solution, only H plus and Cl minus exist in the water. HCl, like this bonded together, does not exist. But when you dissolve HF into water, you will actually see HF, H plus, and F minus present in water, where you do get some ions, just not as much if it were a strong acid. And so that's why we call it a weak acid. So weak electrolytes do conduct electricity, just not as much as a strong counterpart of it, right? So yeah, all three of these substances exist in a solution of HF. All right, okay, so let's actually answer this question then. So let's go through these. KOH, is it a strong, weak, or non-electrolyte? And let's talk about why. It is strong, yeah, why? It's ionic, yeah. Also, it's a strong base, but all of our strong bases are ionic too. So you could, if you go back to this, like, you know, the strong category, it's all ionic compounds and strong acids and strong bases, but strong bases are ionic. So that's why I don't write it twice. All right, HNO3, what is that? It's strong because it's a strong acid. I'll just put SA. Okay, H2SO4. Strong also because it's a strong acid. H2SO3. Weak, yes, it's an acid, but it's a weak acid. So it will a solution of sulfurous acid conduct electricity? Yes, it will, but will it as much as like a 1 molar concentration of sulfuric? No, it won't. So it'll conduct electricity, just not as much. Okay, SO3. Non, yeah, how is that non? It's molecular. If you just try to name it, SO3, if this was chapter 2, you would name it using molecular naming rules, right? You would say sulfur trioxide. So this is, it's molecular. All right, so that is a non-electrolyte. Okay, NH3. Weak, yeah, because it is a weak base. It is the one weak base we have you memorize. Don't worry, when you take 1220, you will learn many, many more weak bases. Okay, calcium chloride. Strong, yep, because it's ionic. And then this thing. Non, yeah, because how do you name it? It's a simple organic compound. This is methanol. And so it's composed of all nonmetals. So there's the rule, all nonmetals, molecular compound. It is a non-electrolyte. Okay, so that's just identifying it based upon the name. So let's take it further and relate, you know, not just naming, okay, is it a weak, strong, whatever type of electrolyte. Let's look at a solution of ethanol. Which one of these pictures is it gonna look like? There's also a none option. So we'll just take it a step further, where it's still the same thing. Identify, is this substance a strong, weak, or non-electrolyte? And then think about what would it look like. What do we think? What? It would be none of them, yeah, because ethanol is what kind of electrolyte? It is a non-electrolyte. So let's just go through all of these pictures and determine what kind of electrolyte's being depicted. So A is depicting what kind of electrolyte? Weak? Yeah, so here, this is an example of like what HF would look like. Here's an HF molecule intact, here's an F minus, and here's a H plus. So see how all three of those species exist in this picture. So this would be like an example. If the question said which one is HF, A would be the answer for that. B is what kind of electrolyte? Strong, yeah. Someone give me an example of a compound that would look like this. HCl, yeah. Give me another one that's not an acid. NaCl, yes. So we're working backwards now, yes. Because HCl is a strong acid, NaCl is ionic. Both of those are strong electrolytes. All right, C, what kind of electrolyte is that? It is also strong. So is this HCl? No, it's not, because there's another detail here about the ratio of cations and anions. So can someone tell me an ionic compound that would look like this? Yeah, so it looks like we have 2 cations for every 1 anion. So it needs to have a formula that looks like this. So it could be something like sodium sulfate. Sodium is a +1, sulfate's a -2. So this would be like an example of sodium sulfate. All right, Okay, so those are electrolytes. Okay, so let's relate this. Okay, so some folks said calcium chloride. So I want to just show that calcium chloride actually does not fit this picture, and I'll show you why. So calcium chloride is a strong electrolyte, right? So calcium chloride looks like that. But when this dissolves into solution, how many moles of cations do you get? How many calciums do you get? You only get one. So you get a calcium 2+, and then you get 2 chlorides. So when calcium chloride dissolves, you get 1 cation, 2 anions. But does this picture show that? No, it shows 1 anion, 2 cations. So you're right in that we need the 2-to-1 ratio. It's just not the right ratio. All right. So that's a small detail. Okay. So let's put this all together and write a net ionic equation for a reaction between, what is this? Acetic acid and strontium hydroxide. All right. So acetic acid is an acid. Strontium hydroxide is what? It's ionic, but specifically it's a base, like sodium hydroxide, potassium hydroxide. Strontium hydroxide is also a base. So if an acid and a base react with one another, that is a neutralization reaction, right? And so we just need to combine these two things and kind of predict what comes out. So we have acetic acid. It's aqueous. We are combining it with strontium hydroxide. That's aqueous. And we figure out what we make. But the hint is here, if this is an acid-base reaction, what is one of our products? Usually it's water. Yeah, water is usually our product. So neutralization reactions fall under the category of double displacement reactions. So we just need to swap our ion partners, right? So if we think about the charges of these things, H+ is positive. Acetate is a -1 anion. Strontium has what charge? 2+. Yeah, you can tell it from the periodic table, or you can tell hydroxide has what charge typically? -2, and because there's 2 of them, strontium has to be +2, right? And so these ions are just going to swap partners. So strontium's going to go with acetate, H+ is going to go with OH. So we can see our 2 products, and do make sure you write it the correct way where it's cation then anion. So our first product is HOH. What is that? It's H2O. So don't write HOH. Yes, that's cation anion, but this is in fact water, H2O. All right. Then the other product, do make sure that it's charge balanced. All right, so if we're combining a strontium and an acetate, what's the ratio we need to make it charge balanced? Yeah, we need 1 strontium and 2 acetates. So make sure that your product is charge balanced. So we get strontium, acetate, and 2 of them, and that's aqueous. Actually, I don't know if it's aqueous yet. All right, I actually don't know the state of it yet. All right, so we have the products. So let's predict the states, so of each of them, meaning is it solid, liquid, aqueous, whatever. So water is what physical state? It is a liquid, yeah. So that one is not on the table. But strontium acetate, we need to figure out, is this a solid or is it aqueous in water? How do we figure that out? We use the solubility table. Yeah, so let me bring up the solubility table. Give me a second. Is it here? Helpful? No. Dang it. Okay, give me a second. Let me just bring up. Okay. Term 2 resources. Let me just bring up. Okay, here's the scratch paper. So this is what you will get on the exam. All right, so using this solubility table, we can figure out whether strontium acetate is a solid, liquid, or gas, if it's a solid or aqueous when it's dissolved in water. So how we read this table, if your substance is at the top, we're kind of looking at it in terms of anions. we see that all acetate-containing compounds are soluble in water. So that means that strontium acetate is soluble in water. So what physical state designation should it get in the equation? Aqueous, yes. If it fell under the second category here, then it would be a solid. But if it would be a solid, then that is in precipitation reactions. All right, so let's just go back to the thing. All right, so that's how we know that strontium acetate is aqueous. All right, so that's not something to memorize. You will be given that table so you can figure that out. All right, so there is the reaction. It's not balanced yet then. So balancing is the last thing we have to do. And so I'm just gonna delete this for clarity. So now that we have all of the substances identified, they're all charge balanced, we can go ahead and balance it. So I see that there's 2 acetates that I need on the product side. So I'm gonna put a 2 in front of the acetic acid. So then I have 2 acetates. Yeah, the best way, just balance the ions themselves. Don't try to like balance carbons and stuff. There's going to be 2 acetates on each side. There's going to be 2, like, 1 strontium on each side. There'll be 2 hydroxides on each side. So we see that, we combine 2 H pluses to 2 hydroxides. So then how many waters would we make? 2. Yeah, so now it is balanced. Okay. No, yeah, I said that you get the solubility table. This is the exact packet that you're gonna get, all right? It is in your best interest to look at this in your course, midterm preparations page to know exactly what you will get, all right? Okay, whoops. So let's go back to this. All right, so this is the balanced equation. Is this the net ionic equation? No, it's not. All right, so in order to get the net ionic equation, we need to think about what these substances actually look like in solution. So once you have your balanced chemical reaction, we need to start splitting up anything that's a strong electrolyte and dissolved in water. So the rules are, once you have your balanced chemical equation and you want to work towards a full or net ionic equation, what you want to do is you want to split anything that is both a strong electrolyte, and it has to be aqueous. All right, so you need both of these things. They have to be both of those things. If it's a strong electrolyte and it's a solid, do you split it up in the total ionic equation? No, it has to be both. It has to be both a strong electrolyte and dissolved in water. It has to be aqueous for you to split it. All right, so this is acetic acid. Do we split this? It's aqueous, but is it a strong electrolyte? No, it's a weak electrolyte. So do we split it? No, we don't split it. So I'm gonna just say no split because it is a weak electrolyte. All right, strontium hydroxide, is it aqueous? Yes. Is it a strong electrolyte? Yes. So do we split it? Yes, we do. So we split that one. Okay, cool. Water, do we split that? No, it's molecular, it's a liquid. These are our rules. These are the only things that we split. What about strontium acetate? Do we split that? Yes, because it is aqueous. And see how the solubility table is important here. It is aqueous and it is a strong electrolyte. So we do split that one. Split, water is no split. Okay, so now we get to our total ionic equation where we just rewrite everything with those splits that we have to do. So if we're not splitting something, all we do is just rewrite the thing. So here is two acetic acids. All right, just rewrite it. Okay, so we're gonna split that strontium hydroxide. So when strontium hydroxide dissolves in water, you get 1 strontium 2+, and you get 2 hydroxides. All right, then we split water, or no, we don't split water, so we just rewrite that, H2Os, and then we split strontium acetate. So we again get a strontium, and we get 2 acetates at the end here. Okay, there we go. All right, so that's our total ionic equation. To get our net ionic equation, we just need to identify our spectator ions in the total ionic equation we just wrote. All right, so a spectator ion is anything that doesn't change from either side. Like you write it the exact same, it's in the same phase and everything on both sides of the equation. So if you look here at acetic acid, it starts off as HC2H3O2, but we see, oh, acetate becomes like a full ion over here. So that means that acetic acid is not a spectator ion. There's actually only one spectator ion in this equation. What substance is it? Strontium, yeah. So strontium is our spectator. So to get our net ionic equation, we just rewrite the thing, but we remove the strontium, anything that's a spectator. So this equation now describes exactly what is going on in this reaction and removing anything that isn't involved in the reaction, and that includes the strontium ions. All right. Okay. Okay. All right. So that is a net ionic equation, right? Those are the tips. And so here, you know, is the idea for getting that total ionic equation. You only split things that are both a strong electrolyte and aqueous. All right, so you can write a net ionic equation for precipitation reactions. You can write net ionic equations for single displacement reactions too. All right. Okay, is there a question? Yeah, you could reduce it, yeah. Okay, all right, so let's keep going. All right, so the second part of reactions in aqueous solution. Yeah, so another one in aqueous solution were single displacement reactions. So that's kind of the second category of reactions that we studied in this chapter. And so within single displacement reactions, us understanding a single displacement reaction will only happen when something is oxidized and something's reduced. So one of the learning objectives in this chapter is to determine what is oxidized and what is reduced in a chemical reaction. And so in order to figure that out, if something's oxidized or reduced, is to understand, how do I determine the oxidation number of a substance given, or the oxidation number of an element or an atom given a substance. And so that'll help us determine whether something is oxidized or reduced, depending on how the charge changes. And so, at least for my class, I tell them oxidation number is really, really closely related to charge. Just think about what would the charge of that atom be in that compound, with a couple rules. Basically, if you're talking about something that's in its elemental form, so if something's in its elemental form like O2 or like magnesium solid, all of these things have a 0 oxidation number because there's no charge. It's oxygen gas is charge neutral, magnesium solid is charge neutral. So all of these have 0 oxidation numbers. But when things are in compounds, then there are charges associated with it. So we see here the oxygen atom in O2 has an oxidation number of 0 because it's in its elemental state. But once we have formed compounds, we can actually calculate the oxidation numbers of the individual atoms. So for this compound, let's just figure out the oxidation number of everything. And again, if you just think charge, you'll be 99% correct most of the time. And so if we think about this compound, it's sodium carbonate. We know sodium carbonate is an ionic compound. So this sodium already has a charge associated with it. What's the charge of sodium usually in an ionic compound? Na+, yeah, so that sodium actually has an oxidation number of +1. All right? So now we need to figure out the oxidation numbers of everything else. And so the tips is if there is oxygen in a compound, it usually has the oxidation number of 2-, like 99% of the time, all right? When it's in a compound, or if you have hydrogen in a compound, it usually has the oxidation number of +1. And that's gonna help us figure out the oxidation numbers of other stuff that's less easily predictable. So we can use that oxygen rule here to figure out what does that oxidation number of carbon have to be for all of the oxidation numbers to add up to 0, because this compound is charge neutral. So I kind of just like set up an equation to figure out what does carbon have to be. I know that there's 2 sodiums and each of those are +1. I'm trying to figure out the oxidation number of carbon. I have 3 oxygens. Each of those oxygens have what oxidation number? Not 2, it's -2. Yeah, so that's important here, -2. And all of those oxidation numbers have to add up to 0 because this compound is charge neutral. That's why, right? So do the math for me. What is the variable? What is it? 4? Yes, so carbon has an oxidation number of +4. So you can check yourself, add up all those numbers and see if they add up to 0. So we have 4 + 2 from sodium, -6 coming from oxygen, it equals 0. So that's the oxidation number of carbon, all right? Let's just do one more. Tell me, what is the oxidation number of sulfur in that thing? So we can set up another equation to kind of figure it out. What's the trick here? What's the oxidation number we already know? Oxygen, yeah, because oxygen's in a compound, it's going to have an oxidation number of -2. So I guess the equation I can set up to figure it out is whatever sulfur's oxidation number is times 4 of the -2's coming from oxygen has to equal what? 0? No, it has to equal -2. It has to equal the overall charge of the compound. So in this case, because it's an ion, is -2. All right, so what is the oxidation number of sulfur? +6, and that's how we do it. Okay, great. So let's actually put it all together and figure out what is being oxidized and reduced in this compound. So literally, we just need to figure out what are the oxidation numbers of all of the elements, then go ahead and figure out how it is changing, all right? So my strategy is let's just get the oxidation numbers of everything. All right, iron, what's the oxidation number of that? 0, how do we know? It's an element, yeah, it's an element, it's a solid, yeah, okay. Tin, what is the oxidation number of tin? Just think charge, it is +2 because tin is attached to sulfate. And sulfate always has what charge? -2, yes. So I'm just gonna skip sulfate for now. Let's look at the tin over on the product side. What's the oxidation number of that guy? 0. And then what about the iron in iron sulfate? +2. So I actually skipped over sulfate. All right, we don't really need to figure out the oxidation numbers of the sulfur and the oxygens in sulfate because they're not changing. Sulfate, see how it's sulfate on each side? It's like literally the same compound. It's sulfate on the reactant side, sulfate on the product side. So will the oxidation number change? No, it's not. Actually, if we did the net ionic equation for this, we would see that sulfate is a spectator ion. If it's a spectator ion and it's not changing from reactants to products, its oxidation number isn't going to change. So I'm not going to spend time getting the oxidation numbers of that, all right? Because I know that oxygen, I guess I will. -2, oxygens is -2. And actually, we just calculated it. What is sulfur's oxidation number? We just did it. It's +6. So is sulfur being oxidized or reduced here? No. Is oxygen being oxidized or reduced here? No. So it's not part of the redox reaction. So what is being oxidized in this reaction? Iron is. Iron actually has an oxidation number that's changing. So iron is being oxidized, and then tin, because we see its oxidation number go down, it's getting reduced, is reduced. All right, so that is how you do it. Okay, how do you know if an element is in its elemental form? So examples: aluminum, solid; magnesium, solid; hydrogen, gas. So it's what the element would look like if you just had the element in your hands. What would it look like? Like gold, solid. All of those are, all of these have 0 oxidation states. But if I had aluminum chloride, That's not an element, that's a compound. Aluminum now has a +3 oxidation state because it's not an element anymore. Okay. Yeah, so those are just like some examples, or like sodium solid, I don't know, oh, tin solid, I guess, in this example, would be examples of things with 0 oxidation states. All of these are elements, elements already. All right, okay, so let's fill in the blanks, I guess. In this reaction, blank is being reduced and blank is being oxidized. So in this reaction, what's being reduced? Tin is being reduced. So tin 2+ in tin sulfate is being reduced. And then iron solid is being oxidized. Okay. And then another way we can ask this question is not just what's oxidized, what's reduced, but we can ask what is the reducing agent, what is the oxidizing agent. In order to reduce something, that thing needs to gain electrons. So that thing, something has to give up electrons to reduce something. So that is what a reducing agent is. So how we determine agents is we just swap these. So whatever is oxidized is the substance that's the reducing agent. Whatever thing that is reduced is the oxidizing agent. So to answer this question, we just swap them. So since iron is oxidized, iron solid is our reducing agent. And because tin is being reduced, it is our oxidizing agent. All right. So that's just another way we can ask the same question. Instead of asking, what is being reduced in this reaction? Instead, I could ask you, what is the oxidizing agent in this reaction? And it's the same answer. You would say it's tin. Okay. In the questions on the practice that said carbon, graphite, what does that mean? That doesn't come until chapter 5. Okay. All right. So let's quickly do some calculations and then we'll move on to chapter 5. But actually, why don't we just what would the oxidation number of carbon solid graphite be? It would be 0. What about carbon solid diamond? What would the oxidation number there be? 0. Yeah. They're both elements, just charge neutral elements here in the solid phase. So both of these would have 0 oxidation states, but the solid, or like the difference between graphite and diamond, doesn't come up until chapter 5. So that's not related to chapter 4, although we can still calculate the oxidation numbers of those things. Okay, so I started this chapter, or this discussion, about molarity and relating it to stoichiometry. So let's just finish these up. These calculations, because a lot of that is what we just went over was more conceptual. But we introduced this idea of molarity, which has the unit big M, but a big M is hard. It's hard to think about what does that actually mean. And at least for my class, I told them, go to bed tonight and say 100 times, molarity means moles per liter. Moles per liter. To calculate the concentration of something, if you count how many moles of stuff you have over the liters of solution you have, that's how you calculate the concentration, all right? And so we can use this concentration as a conversion factor also in dimensional analysis to figure out how much stuff do we have present in a given solution with a known concentration. So in this question, we have 15 milliliters of a 2.5 molarity calcium nitrate solution, right? We transfer this into a 500 milliliter volumetric flask, and then water is added to the calibration line. What is the concentration of nitrate in the flask in molarity? Okay, so this is a dilution equation. So the equation for dilutions is M1 V1 equals M2 V2, where M1 and V1 are the solution that you're diluting. It's the small amount of like substance that you put in the volumetric flask before you add a bunch of water. V2 is what the final concentration of that solution is. Because when you add water to a volumetric flask, you're not actually changing the amount of solute particles present, you're just changing the volume of water that all of those solute particles have to dance around in. And so, that's why we call it dilution. You have the same amount of stuff present, they're just present in a larger volume. Right? So we can go through all these pieces of information and kind of categorize it. Is it M1, V1, M2, etc., given this prompt here. So 15 milliliters of a 2.5, this is our concentrated solution. So to me, this sounds like V1 and M1 is right there. So 15 mils and then 2.5 is M1. So if I draw, I guess I can draw a picture, right? You put 15 mils of that concentrated stuff in your volumetric flask. So you transfer like a set amount of calcium and nitrate, and then we dilute it to 500 milliliters. So this is V2, right? So we can just plug in these numbers into our equation to get the concentration of our diluted solution. So since both of these volumes are in milliliters, we don't actually have to convert them to liters. It's okay, we can just leave them there as long as the units on each side of the equation match. So I have 2.5 molarity of calcium nitrate. All right, we are diluting 15 milliliters. We are solving for the new diluted concentration. So we're solving for M2 in this case. And then our new concentration, or sorry, new volume is 500. No, I don't, different color. 500 milliliters. All right. I dropped a bunch of my sig figs. There we go. So our answer should have 3 sig figs. All right, I didn't even, what's my answer? Okay, what is my answer? Okay, so we get that M2 is equal to 0.0750 molarity, but that's the molarity of what? Calcium nitrate. So is this my answer? Not hydroxide. No, it's not, because what does this question ask me? We want the concentration of nitrate, not of calcium nitrate. So because I put into this equation the concentration of calcium nitrate, what comes out on the other side, M2, is also the concentration of calcium nitrate. But if we think about when we dissolve calcium nitrate in solution, we get 1 calcium ion, but we actually get 2 nitrate ions. So in order to get our correct answer, we need to multiply our answer by 2, but there's a reason for this. I can do the dimensional analysis here. 0.0750 moles of calcium nitrate is present in 1 liter. That's what that molarity value means. All right, so I want the concentration of just nitrate. So to do that, I can just look at the formula here and say, oh, for every mole of calcium nitrate, I actually have 2 moles of nitrate present, nitrate. All right, so that's why I have to multiply my answer by 2, all right, and then whatever answer that is, all right? So if I told you that you had a 0.50 molarity solution of aluminum chloride, tell me, what is the concentration of chloride present in the same solution? I tried to make the numbers easy, using the same concept here. This concentration is telling us how much aluminum chloride is present, but if we look at just chlorides, how much more chlorides are present than just aluminum chlorides? There's a factor of 3. Yeah, so what is the concentration of chloride present? 1.5, yeah, molarity. Yes, 1.5. What if I told you that you have a solution of calcium chloride, all right, with some unknown concentration, I don't know what it is, but I tell you that, oh, you measure how much chloride is present, and let's say it is 2 molarity. What is the concentration of calcium chloride then? 1, yeah, so it would be 1 molarity in this case, because I'm telling you the concentration of this thing, but to backtrack it back to the original substance, it would be 1 molarity. All right, so it's all related to the superscripts here and what these substances actually look like in solution. Okay, good. Very good. So do be sure that you check, what the question is asking in the question. All right. Okay, so let's do this titration. Okay. Do I want to do a titration? Yeah, let's just do the titration. Okay, so we titrate a 20 milliliter sample of phosphoric acid, and it requires this much base to reach the endpoint. All right, so this is very similar to your LLT lab. And I tell you that phosphoric acid is a triprotic acid. What is the concentration of phosphoric acid in the original sample? So it's asking for concentration, so that's a molarity. It's specifically asking for concentration of phosphoric acid. So in order to get the concentration of phosphoric acid, I need to figure out how many moles of phosphoric acid I have and then divide it by the volume of phosphoric acid I have. So if I figure out the moles what I have and the volume of I have, I can figure out the concentration. Did the question give us one of these already? Yeah, which one? The volume. Didn't they already give us the volume? How much volume of phosphoric acid are we playing with? 10 milliliters. Yeah, it says I'm titrating a sample of 20 milliliters of phosphoric acid. So I already know that number. That number is 20 milliliters, right? Convert it to liters before you do the calculation, but we already have that number. Now we need to figure out how many moles of phosphoric acid I have, and I'm going to figure that out from figuring out how many moles of sodium hydroxide I reacted it with. But I also have to use stoichiometry as well, right? Because the detail in this question I glossed over, as I said, phosphoric acid is a triprotic acid. So I can just kind of make it easier on us and just write phosphoric acid as H3A, meaning that there are 3 acidic protons on this acid. So if there are 3 acidic protons on that acid, how many moles of base do I need to neutralize it? Don't think that hard. 3, yeah, right? So we need this stoichiometry to figure out how much phosphoric acid is present, because the question gives us how much sodium hydroxide we have. So then we can use stoichiometry to figure out, okay, if I know how much sodium hydroxide I have, it's a 3-to-1 ratio to get to phosphoric acid, all right? So, a reaction's happening, we're making water, but we don't actually really care about the products. All we really care about is this relationship right here, that for every 1 mole of phosphoric acid, I need 3 moles of sodium hydroxide to neutralize it. All right, so this is our stoichiometry that we'll use, but first we need to figure out how many moles of sodium hydroxide are present, and that's from the last piece of information we didn't use yet. And so I can write there's 18.75 milliliters of sodium hydroxide reacting. I'm going to convert that to liters. So there's 1,000 milliliters in 1 liter. Right, and so remember, this is liters of sodium hydroxide. I always like to tell students to rewrite molarity values as a conversion factor to help you see how the units work out. Remember, molarity means moles per liter. So if I tell you that there's 0.811 molarity sodium hydroxide, what that means is that there is 0.4811 moles of sodium hydroxide present in every 1 liter of solution, right? So that's a derived unit. So remember, how units that have fractions in them, the value goes with the top unit, and then the bottom unit gets that implied 1. And so if you don't believe me, if I say, okay, if you're driving 65 miles per hour, if we wanted to write an equality that would help us do dimensional analysis, you could write in every 1 hour, how far do you go? 65 miles, yeah, 65 miles. So see how the top unit gets the number, and then the bottom unit gets an implied 1. And that's exactly how this molarity works as well. Because remember, molarity means moles per liter. So that means 0.4811 moles of sodium hydroxide equals an implied 1 liter of solution. Okay, so with that molarity conversion, you can see, am I going to put the 0.488 on the top or the bottom here? So the units cancel. Right now I'm in the unit of liters, so I want to put liters on the bottom. And then I want to put 0.4811 moles of sodium hydroxide on the top. All right, so did I calculate the number of moles of phosphoric acid I need yet? Nope, not yet. Because right now, if I finished right now, I would be in the unit of moles of sodium hydroxide. I want moles of phosphoric acid because I'm asking you the concentration of phosphoric acid. So I take this value, and this is where I do stoichiometry, where you need 3 moles of sodium hydroxide in every 1 mole of my triprotic acid, phosphoric acid. All right. So, so there we go. So this is the mole amount that we have reacting with phosphoric acid. And based upon this much sodium hydroxide that's reacting, 0.003069 moles of our triprotic acid has reacted. All right, and so that's not the answer we want. This question is actually asking for a concentration of phosphoric acid. And so we need to divide by the liter amount of phosphoric acid we initially titrated. So we're dividing by 0.02000 liters, and then we get our concentration there of phosphoric acid. All right, so yes, I see it in the chat. It says, my professor told me titrations on the test. Okay, titrations is just an application of solution stoichiometry, right? We're still using all of the same skills for non-titration solution stoichiometry questions, right? It's just saying the word titration makes it sound like you know, you're using a burette like you did in lab. I could rewrite this question so I don't use the word titration, and it would still be fair game on the exam. I could say 20 milliliters of a triprotic acid with an unknown concentration requires this much to neutralize it. What's the concentration? Bam, now it's not a titration, right? So this question has all of the same skills that all the solution stoichiometry questions have, where we have concentrations, we have to consider what is the balanced chemical equation. We're using volumes now and concentrations to figure out mole amounts of stuff. Remember back in chapter 3, we would give you gram amounts of reactants. To get to moles of reactants, what information did we use to get to from grams to moles? We used molar mass. But in this chapter, we give you volumes and concentrations to give you mole amounts, right? So that's the big difference in this chapter, is now we're using concentrations. Okay. All right, so there we go. Okay, so we did chapter 4 enough, so let's just skip this question. It's on the key. Okay, so it's just more solution stoichiometry. All right, all the same skills. So remember, molarity means what? Moles per liter. So 2 molarity sodium hydroxide means there is 2 moles of sodium hydroxide in every 1 liter. So 2 molarity magnesium chloride means that there are 2 moles of magnesium chloride present in every 1 liter of solution. So that means, look, I tell you the volume. We have 1 liter of this concentration of sodium hydroxide. How many moles of sodium hydroxide are present, are reacting right now? 2, yep, 2. How many moles of magnesium chloride are present? 2, yep. And then at that point, you could do a BCA table or something to figure out the limiting reactant. Okay, All right, so let's move on to chapter 5, where we talk about thermochemistry, energy of chemical reactions. I do want to do this question. Okay, in which of these scenarios does potential energy decrease? So remember, as chemists, we think about potential energy in terms of charges. All right, so potential energy is related to two charges interacting over the distance between those charges. So if you just think about magnets. Like if you have oppositely charged magnets, typically we say that those magnets are attracted towards one another. The attraction is stronger when they're close together versus when they're far apart. If you have two negatively ended magnets and you try to bring them together, what do we call that? Repulsion, yeah. And so you can draw a graph that might help you depict attractions and repulsions. Attractions happens in the negative region, all right? So in chemistry, yes, we can have negative potential energies, and they're actually favored. We want negative potential energies for compounds because that means things are stable. So this is our attractions region, and then up here in the positive potential energy realm, this is repulsions. Repulsions. So we see, if we think about what this means, it means like if you bring two negatively charged particles, bring them together, those two particles are what? Attracted or repelled from one another? Repelled, yeah. Will the repulsion get stronger or weaker as you bring them together? Stronger, yeah. So think about trying to bring two negatively charged particles together. You have to put energy into the system. We have to physically push them together to make it happen. So that's why this graph, as D decreases, as you bring them closer together, if we're in the repulsion realm, potential energy goes up because we have to put energy into the system to bring two repulsive things close to one another. Versus if we're in the attraction realm, right? Two attracted things, if we bring those two things together, they'll come crashing down into one another automatically if you bring two attracted things close to one another. So much that their distance just, it goes to zero, that they, go towards one another. Right, so that's how I think about potential energy. If you put in the signs of Q1 and Q2, this is the graph that you get, right? Where this region is negative, and then this region's negative, and this region is positive and not very favorable. Okay, so let's think about these changes. What happens to potential energy when we bring two positively charged particles closer together? So I like to think, once you have this graph, think, okay, this question is talking about two positively charged particles. So are we in repulsion or attraction? Repulsion. So that means we're looking at this graph. We're bringing them closer together. So are we going left or right on this graph? We're going left. We're going closer to the, or we're going closer to the y-axis. So we're going to move this way up the graph. And so tell me, does energy go up or down when we go left across the graph? It goes up. Yeah, so since it goes up, potential energy is going up. So that's not one we want, because what are we looking for? Instances where potential energy decreases. All right, so that one's not it. All right, what if we reduce the speed of a charged particle? How does that change potential energy? Or does it? Is speed in this equation? No. So will potential energy change if we change the speed? Nope, we won't. Nope. What does change? Kinetic energy. Yeah, so I'm trying to trick you here. All right, to think of, just some students will just generically think of energy as both potential and kinetic at the same time, but no, if we change the speed, we're just changing kinetic energy, not potential. How would kinetic energy change though? If we're reducing the speed? It's gonna decrease because kinetic energy is described by 1/2 mv squared, and so if we reduce the velocity, kinetic energy will go down. So that one's not it. All right. Energy goes down, but it's kinetic energy, not potential. All right, what if we bring two negatively charged particles closer together? Is this attractions or repulsions? Repulsion, so we're up here. So if we bring them closer together, does potential energy change? It goes Use your hand, it goes up. Yeah, so C is the same as A. We're bringing two repelling things together, potential energy goes up. All right, bringing two oppositely charged particles closer together. So is this attractions or repulsions? Attractions finally. So we're here. If we're bringing them closer together, we're moving left across the graph. So does potential energy go down? Yes, it does. So here is our answer. Yes. Okay, but let's just finish it. So this last one, let's double the charge of two separated negatively charged particles. So doubling the charge of two negatively charged particles. So if these are negatively charged, are we in attractions or repulsions? Repulsions, yeah, repulsions. And so I guess the best way for me to describe this one is, remember, the equation for kinetic energy is Q1, Q2 over distance. So we're not changing distance here. So let's imagine our particles are positively charged. Let's say they're +1. So we have +1 over some distance. There's the potential energy of the first state. If we double the charge, what is the new charge of this first ion? +2. Yeah, so now Q1, Q2 is going to be +2 times +2 over distance. So these are our two states. So tell me, how does potential energy change from going from this to this? It's going to go up. Yeah, because we have just a +1 on the numerator in this one, but a +4 in this one. So we see potential energy go up. So that one's a tricky one, but we see potential energy does go up there. Okay, so there is some conceptual stuff with thermochemistry. Okay, so yeah, let's do question 10. The activity series is not on the info sheet. We're trying to be there for the exam. Is that a mistake? No, so we are, if you need the activity series for a question, it will be in the question. Okay, all right, so because that is not something that any real chemist would dare to memorize. And so that means you guys would never have to memorize it. Just know how to use the table. All right, so for 10, we're still talking about energy here. So which of the following processes does internal energy for a system always positive? So delta E. All right, so the equation to calculate change in internal energy is, does anyone know? Is it given on the supplemental information? Because if not, you might have to memorize it. Is it? Huzzah! No, it's not. So the equation for the change of internal energy for a system is equal to all of the work and heat, yeah, W and Q for that system. All right. Okay, system. But the tricky part here is getting the signs right. All right, getting the signs right. Okay, so we just need to, I tell my class at least that in chapter 5, if you're going to get a question wrong, it's because you messed up your sign. Right, and the reason a lot of students, and me too, I oftentimes mess up my sign, is because I'm selfish. And I think about when heat is involved, I think about, oh, how do I experience that heat? But that's not what these variables are talking about. Q system means how does heat in the system change? So usually that's the reaction, right? So when we do like the hydrogen balloon experiment, you know, it's a big fiery blast, right? We love it, right? So when it's a big fiery blast, we experience that heat that's given off, but that energy that's given off is actually lost by the chemical reaction. So that's an exothermic process. The reaction loses heat. So that overall process is actually negative for the reaction, even though we experience a positive energy change there. So we need to always be thinking about how are the energy changes changing with the system, not us. So for example, I try to be very clear with my language here. If a system absorbs heat, if it absorbs heat, what is the sign of Q of the system? It is positive, yes. If if a system absorbs heat, what do we experience? If we're holding the system and it absorbs heat, where's that heat coming from? Your hand. So what is it going to feel like? It's going to feel cold. Yeah, but Q is positive, but it's getting cold. So again, make sure that you're thinking about what are these signs with respect to the system, not yourself. Okay. Okay, then work of the system, and it expands against an external pressure. All right, so work is a little bit trickier to get. So work, I like to think of it, work for a system is positive if you squeeze the heck out of it and make it smaller. But when a reaction does work on its surroundings, that's a negative work value, and it usually expands against, it gets bigger, like a piston going up or something, and that would be a negative sign of work. There's an equation for it also. You can think, oh, work of your system is equal to negative pressure, but that's a constant, times how its volume is changing. All right, if you want an actual equation. So you can see here, if the volume gets smaller, delta V is negative, work ends up being a positive number. When the volume of your system gets bigger, if it expands, delta V is what sign? Positive, but then work is what sign? Negative. Yeah, so this might be something useful to, if you like numbers, if you like equations, to think about getting the sign of work of your system correct. Okay, so work of your system is then what sign for this example? Expands against an external pressure. It would be negative, yes. Okay, so these two values, when we add them up, will be our change in internal energy. All right, so let's just do all of them. Okay, a system loses heat. What's the sign of Q? Negative. What would we feel if a system loses heat? We would feel it get warmer, yeah. What is the sign of work? It's negative again, yeah, it expands, okay. So when you add a negative number to a negative number, you will always get a negative number, yeah. So this example, B, is we can say for certain, is a decrease in overall internal energy for this reaction. But is that what this question is asking for? No, we want the positive version. Right, so we're looking for an example where both Q and W of the system are positive numbers. So let's keep going. A system absorbs heat. So what is the sign of Q? Positive. It contracts. So what's the sign of work? It is negative in this case, because contracting implies that volume is a negative value, or the change in volume is a negative value. So that means that work of the system is going to be a positive value if you just plug it into this equation. Or if you think in order to make like a gas smaller, you have to like squeeze it, you have to put work into that system to make that happen, right? Oh wait, that's supposed to be a positive, right? Volume contract, yes, that's positive. Okay. So when we add two positive numbers together, you will always get a positive number. So that is our answer. C is an example when something absorbs heat and contracts, it is always a positive change in internal energy, always. Okay, but let's just finish this off. A system loses heat. So what is Q? Negative. And it contracts. What is the sign of work? Positive. All right, yeah. And so those two things, when you add these two things, I would have to know the magnitudes in order to get the sign of change in internal energy. All right, so I could actually give you numbers here too, and you would calculate the value of delta E given the terminology here. I could say a system loses, okay, let's just do that. Let's do that. Let's say a system loses 10 kilojoules of heat and contracts due to external pressure and has 20 kilojoules of work. All right, so those are the values. Tell me, what is the value of change in internal energy? Do I just add 10 and 20 together? No, we got to get the signs right. So if this system loses 10 kilojoules of heat, is Q Positive or negative? It's negative, yeah, so it's not 10 kilojoules, it's negative 10 kilojoules. That would be what Q is. And then if we add work, it contracts due to external pressure with 20 kilojoules. So is work 20 kilojoules or negative 20 kilojoules? It is 20, yeah, so it would be 10, negative 10 plus 20 kilojoules. And so the answer would be just 10 kilojoules. And if that was on an exam, there would be tons of options, tons of iterations. There would be 30, there would be negative 30, there would be 10, negative 10, all of those. But there's only one where you get the signs correct based upon how this is worded. Does the system lose, or does the gas expand, or do work, or has work done on it? So we got to be thinking about relative to the system. Okay. All right, so there's only some chapter 5 things we need to do. Is there a certain kind of chapter 5 question we want to go over? 17, yes. Yeah, let's do 14, 15. Yeah, let's just work our way to 17, okay? All right, okay. How many kilojoules of heat is required to increase water from this temperature of this temperature? There's a specific heat of water. Okay, so this is an equation you are not given on the supplemental information, and that is Q, so heat involved in a reaction or any process, is equal to mass of the thing that's changing, the specific heat, and its change in temperature. All right, where specific heat has a unit of joule, gram, degree Celsius. So you see how all of these units, as long as you're using specific heat, you need a mass value, a temperature change value. That's how you get heat, which is in the unit of joules. There's another Q we can get also that doesn't use specific heat, but it uses heat capacity. That's just a big C, C delta T. So big C, this is heat capacity, has the unit of joule degree Celsius. All right, so do be sure you're using the right unit. I mean, whenever we give you values, they typically have units attached to them. So here, I tell you the specific heat of water is this. So which equation are we using? The first one or the second one? The first one. Also, I tell you a mass, and I tell you the temperature change. All right, so the tips here, temperature change is always final minus initial, always, always, always. So we just calculate it. So is our temperature change, it's gonna be always final minus initial. So delta T in this example, I think I can do that math in my head. 78, is it 78? Yeah, so it's 78, and it's specifically, it's positive 78 because it's 100 minus 22, all right? So that's delta T, we got delta T. I give you the specific heat, and then do I give you the mass? Yep, I give you the mass right there, all right? So it's just plug and chug here. All right, so the temperature required to heat up this water is 150 times 4.184 joule, gram, degree Celsius, or Kelvin, it doesn't matter, because a delta T in Kelvin and Celsius, they're the same value. And then our delta T is positive 78 degrees Celsius. All right, and so we calculate this to be the heat required to heat up this water is 48953 joules. Excuse me. Obviously the sig figs aren't right, but is this my answer? No, because the question asks for kilojoules, yes. Heating water takes a lot of energy, so it's better to report this in kilojoules. All right, so I'm gonna divide this by 1,000 to get this into kilojoules. How many sig figs do you think our answer should have? Probably 2, yeah, since all of this is multiplication, this mass has 2, our delta T has 2, so it makes sense our answer has 2. And so our answer is 49 kilojoules. Okay, lots of energy to heat up water. That's not that much water. That's like a cup of water. It's like a teacup. It's like a teacup of water from like room temperature to boiling. Okay. All right, let's look at this. Okay, without doing any calculations, I love these. If the same amount of energy is delivered, so Q, same amount of Q, is delivered to 200 grams of aluminum, or sorry, 120, or 120 grams of gold, which one has the final, the higher final temperature? Assuming they both start at room temperature, probably. Yeah, same initial temperature. So I give you that the specific heat of aluminum is 0.88 joules gram degree Celsius, and gold is 0.13 joule gram degree Celsius, or Kelvin, whatever. Right? So the difference here in this example is I'm trying to tell you, oh, we have two samples. The masses of them are completely the same. All right, so I'll just write down here, Q equals MC delta T. Or I memorize it as Q equals MCAT, where the triangle is the delta sign, and then the other Q equation, since I guess you're memorizing this, is Q equals CAT. That's the other one. The first one's Q equals MCAT, and the second one is Q equals CAT. All right, so we are heating both of these things up. We're delivering the same amount of Q. I'm asking you which one ends up at the higher final temperature. Which one do we think it is? Aluminum or gold? Gold. It is gold. Why? Smaller specific heat. Yes. That I like to tell students, so when looking at specific heat, something like water or H2O has a specific heat of like 1.48, while metals have lower specific heats. Just from you and your everyday interactions in life, water is fairly hard to heat, right? So water has a really high specific heat, meaning it takes a lot of energy to change its temperature by 1 degree Celsius. So that's how I think of it. Large specific heats mean that those substances are difficult to change their temperature versus like a metal. Metals, they change their temperature fairly easily. So they tend to have lower specific heats here, right? And an analogy I use to specific heats is imagine you just, you finished a long walk on a hot day, really hot day, sun's blazing. And you come up to some benches, and you have the option to sit on a wooden bench or a metal bench. Which one do you choose? The wooden bench. Why do you choose the wooden bench if it's a real hot day? It's gonna feel cooler. Yeah, won't it feel cooler, the wooden bench? Okay, so tell me, does wood, which one has a higher specific heat? Wood or metal? Based upon your observations, that you want to sit on the wood bench. So does wood have a high or low specific heat? High, yeah, because it's hard to change its temperature. All right, yeah, and so for the same reason here, but opposite, because I'm asking you which one's the hot metal bench is, in this case would be gold, because it changes its temperature much, much more rapidly. Okay, see the analogy? Yeah, all right, great. Okay, so that's without any calculations, but essentially what we did was deconstruct this Q equals MCAT equation. We recognized M is the same, specific heats are different, temperatures will be different in order to keep Q the same. Okay, all right, so those are the conceptual things. So let's do some calculations. Okay. All right, so these two next questions are going to be the hardest questions on the exam. And so my advice to you is to skip these questions on the exam and wait until the end if you have time to do them, because I don't want this to happen, that this is like the third question you get to on the exam and you spend 30 minutes on it and you probably still get it wrong, leaving you only 40 minutes for the rest of the exam. I don't want that, all right? So do not spend the first time around, do not spend more than a couple minutes on this question. Just wait for it at the very end if you have time. Because remember, all questions on this exam are worth the exact same points. So do you want to spend 20 minutes on this question, or you want to do like one of the conceptual questions that'll only take you a minute, right? They're worth the same amount of points. Don't waste all your time on this question. It's better to just leave this at the end. And if you have time, get to it, unless you're really good at these. Okay, but there's a lot of places to go wrong. All right, so we have a salt and it's dissolving in 120 grams of water. The temperature is initially that, increases to that. What is delta H for this reaction, for this dissolution process? All right, so in order to calculate the enthalpy of dissolution for this process in kilojoules per mole, I need to figure out what is the Q, how much heat is involved in this reaction, and then I want to divide by how many moles of stuff I have I'm actually reacting in this reaction. That's how I get it into the unit of kilojoules per mole. Okay, so there's a couple things. This is the strategy. Before doing any calculations, just estimate, predict what the sign of delta H is. We need to predict the sign of delta H. And we do that by looking at the temperature. How is the temperature in the cup changing? It's going up. So that means the sign of delta H is what? Ooh, I hear both. It is negative. This is an exothermic process. You want me to tell you a story? Yeah, okay. Okay, so I've been teaching here for a while. The first time I gave an exam that covered chapter 5 stuff. I did the exam, like once I received it to edit it, I tried to do the exam as fast as I could. As fast as I could. It was chapters 4, 5, and 6, okay? 4, 5, and 6. I did the exam, the midterm, in 7 minutes. And I got one question wrong, and guess what it was? It was this question, but I didn't do the math wrong. I was wrong by what? Just the sign, all right? So for those of you, you see, oh, temperature goes up, delta H is positive. No, no. Yes, you saw the temperature go up, all right? You are part of the surroundings. The reaction is actually losing that heat. So the reaction loses heat, delta H is negative. We observe an increase in temperature. All right, this is an exothermic process, right? So take the half second to just predict the sign that way. Remember, don't be selfish. You are not the reaction. The reaction is the system. You are not the system. So this reaction is losing heat, so we observe an increase in temperature. So whatever values come out at the end, it needs to be a negative value. This reaction loses heat. Okay, now we got half of the points, right, is just getting the sign right. So let's actually get the number, and this is the harder part. All right, so we are utilizing the first law of thermodynamics. If you did the IHT lab, that it should help here. So we're utilizing the idea that heat lost is gained by something else. You need that negative sign there. This is the first law of thermodynamics. Heat lost by something is gained by something else. There's two equations for Q we learned about, right? Q equals MCAT and Q equals CAT. So in this example, we're going to use the Q equals MCAT equation. But there's only one thing that's changing temperature, and that is the solution, right? So when we think about Q lost, Q gained, our reaction is losing heat and our solution is gaining heat, okay? We can't measure heat loss by the reaction directly. We're going to do it indirectly by measuring, okay, how is the heat of the solution, all of that water, how is that changing? Because that's what we're measuring, right? So I can say, oh, Q reaction equals the mass of the solution times the specific heat of the solution, times the delta T of the solution. Those are all things we can measure, and we did measure. I actually gave you all of those values. All right, so what is the change in temperature of this solution? It is these two numbers, final minus initial. All right, so that's delta T here is 30.2 minus 21.6. What is it? What is it? It is 8.6 degrees Celsius. That's delta T. What is the specific heat of solution? Did I give it to you? Yes, it's the same as water, so I have that value too. What is the mass of the solution? This is, if you're going to get this question wrong, you're going to get it wrong right here. What is the mass of the solution? What's in your cup? Is it 120? No, it's what? 126.23. Yes, it's everything in the cup. You have 120 grams of water, but then you put 6 grams of junk in it. Now you have 126 grams of stuff that you're heating up, right? So the second next to the sign, okay, next to the sign, the next place that you would mess up is right here, where you would put 120, but it's not 120. The mass of the solution is actually 126.23. It's the mass of the salt that you're putting in and the water. Okay, all right. So let's do that. So Q reaction equals 126.23 grams. Specific heat, 4.184. I'm going to just drop units. Delta T is 8.6. And so we get Q reaction, negative Q reaction equals, do I have that? 4,542 joules. So this solution gained 4,000 joules of heat. That makes sense. It got hotter. It gained 4,000 joules of heat. Where did that heat come from? The reaction. So the reaction lost, so I'm going to just move the negative sign now. The reaction lost 4,542 joules of heat. All right, there's that negative sign. Okay, so this is Q of our reaction, but that's the Q of this specific reaction where I only react 6 grams of stuff. I want to convert this in a per mole basis, and so to do that, that's where I use delta H equals Q reaction over the mole amount that I actually reacted. So I'm going to just convert this into kilojoules right now. So negative 4.542 kilojoules. How do I get the mole amount of stuff I reacted? The gram amount and the molar mass. Yeah, that's it. All right, so I'm going to take that gram amount. So 6.23 grams of calcium chloride. Molar mass is like 111. 110.98 grams is 1 mole of calcium chloride. And whatever that answer is goes in the denominator. All right, so just divide by the mole amount. And then that's your answer scaled to a kilogram per mole. And then what is the sign of this delta H value? Negative, yeah. So do see how that negative did propagate. I'll just write the answer. What is it? It is negative 81 kilojoules per mole. All right. So definitely 2 places to go. Yeah, so I did this question that first time, 7-minute, did the exam, but it was this question and I didn't report negative 81. I just reported 81. I did remember the mass thing. It was just that dang sign, I just half a second, if I just would have thought about it, oh, water gets hot, it has to be an exothermic reaction. It has to be a negative delta H, okay? Versus you throw a salt in, the solution gets colder, so delta T is negative. What is the sign of delta H there? If the water gets colder, it's positive. Yeah, that's an endothermic reaction. It works the exact same way. As long as you are using this equation, negative Q lost is positive Q gained somewhere else. Always do final minus initial. You'll never be wrong. All right, so there's that one. Okay, so the other hard one. So we'll do this one. Okay. Is another way we can calculate delta H of a reaction. So we're actually doing the same thing. Delta H of this reaction, we need to figure out what is the Q of this reaction and divide by the mole amount. We're doing the same thing, we're just using a different strategy. We're not using a coffee cup, we're using a bomb instead. So bomb calorimetry utilizes the total heat capacity of that bomb. So you obviously did coffee cup calorimetry in lab, but in this example, this is actually how they figure out how many calories like our foods have. They put it in a little bomb and they like combust it and measure how the temperature changes. So that's what we're doing here for titanium dioxide. Okay, so we combust 2 grams of titanium in a calorimeter, and the calorimeter temperature increases from that to that. The total heat capacity of the calorimeter is that. Calculate delta H of this reaction. So we are still utilizing the idea that the heat lost by something is always gained by something else. So this is the first law of thermodynamics. And just like in the other example, the heat being lost is by our reaction, but this time it's being gained by our calorimeter. Before in coffee cup, it was gained by the solution, but in this case, it's gained by the calorimeter, right? So the big difference in this question, in the previous question, I gave you the specific heat for water. But this question, do I give you the specific heat of something? No, I give you the total heat capacity of the calorimeter, right? So which equation, which Q equation are we going to use? Are we going to use Q equals MCAT, or are we going to use Q equals CAT? CAT, yes, Q equals CAT. So do I know the delta T of the calorimeter? Yes, I figured out. Do I know the total heat or the heat capacity of the calorimeter? Yes, it was given to you. So do I need this mass of water at all? No, you don't. All right, so that's just extra information that I gave you. All right, so in this example, negative Q reaction equals the heat gained by our calorimeter, but we're going to use the Q equals CAT equation instead, where we use the calorimeter constant of our calorimeter times delta T. That's it. Right? We can calculate delta T. It is what? 91.6 minus 25. So delta T is equal to 66.60 degrees Celsius. It is positive because the temperature is going up. Oh, actually, let's use our intuition again. Calorimeter got hot. What's the sign of delta H? Negative, yes. Very good, very good. Okay, so we need to make sure that our delta H at the end is negative. Okay, so we have delta T and we have the calorimeter constant is given right there. So that means negative Q of the reaction, the heat the reaction lost, is equal to 9.84 kilojoules over change in temperature, times that change in temperature, 66.60 degrees Celsius. So we see that the calorimeter gained how much heat? 655 kilojoules of heat. All right, the calorimeter gained that much. So that means the reaction lost 655 kilojoules of heat. Is that consistent with what we thought about before? This reaction has to be what kind of reaction? Endo or exothermic? Exo, in order to heat up the calorimeter, Q is negative. Is that consistent with that? Yes, it is. Okay, perfect. All right, is that my answer? No, it's not. But I like your enthusiasm. This question doesn't ask for Q of the reaction, it asks for delta H of the reaction. So we need to get it into a per mole basis. So this answer is how much heat if 2 grams of titanium reacts. We want how much heat is produced when 1 mole of titanium reacts. So what do you think we do to this answer? We divide by mole, not molar mass, but the moles of stuff we actually reacted. So in this case, we're going to take it just like the last step we did up here, right? It's just the same, where we take, this reaction used 2 grams of titanium. We're going to divide by the molar mass of titanium, so 47.88 grams, 1 mole. And so that tells you that whatever that answer is, all right, we're going to divide by that Q reaction, so negative 655 kilojoules. And then that would be our answer. So whatever mole amount that is, that small mole amount, we divide by that, and we see that our answer is huge. It's like negative 15200 kilojoules of heat per mole. That for every mole of titanium that we burn, this is how much heat is released. It's a butt ton. Okay, so this answer, negative 655, is specific to just 2 grams of stuff reacting. This answer is if a mole's worth is reacting. And these types of numbers are useful for table values, all right, where you want to, figure out how much heat this reaction would release. Having table values and per mole amounts are helpful for calculating that. Okay. Oh, poop. We have 30 minutes. So let's let's do this one. Okay. Calculate the enthalpy of combustion for 1 mole using bond enthalpies. Okay, so we learned how to calculate enthalpy a bunch of different ways. We used coffee cup calorimetry. We skipped over heats of formation and stuff because those ones are straightforward. But this is the last way to calculate heats of reaction, and that's based upon bond strengths. All right, so the information given here is I give you some structures of compounds. I have this chemical reaction. And so you can think of a chemical reaction happening, thinking of it like Legos. All right, we are breaking apart all of these atoms on the reactant side, and we're reforming them into new stuff on the product side. All right, so breaking a bond always has what sign of delta H? To break something. Positive or negative? Always. To break something. Positive, yeah, breaking something always is endothermic, always. If you think of breaking something as just the opposite of forming something, so forming a bond, therefore, is always a endothermic process. Yep. So the new equation, I guess, that we can use to calculate delta H of a reaction using bond enthalpies is take all of the bonds that you break and subtract all of the bonds that you make in a chemical reaction. And that's how you can get the overall enthalpy of that reaction. These are fun. These are my favorite ones because I get to break things. I get to break them. All right. So in this reaction, we are breaking 3 oxygen molecules and all these bonds in this, what is this? Ethanol. Right. So I like to inventory all of my bonds and think, okay, what bonds do I have to break? What bonds do I have to make? I inventory all of them, and then I do the equation, break minus make. That's how I get the overall reaction. So we need to break everything on our reactant side. Think of it like Legos. We start with this stuff. We separate all the little Legos. That costs me some energy. And then I reform the new products, and I get energy back. But let's figure out what the magnitudes of those are. Okay, so let's take inventory of the bonds I have to break. This can be tricky because there's different bonds. So it looks like I have to break a carbon-carbon bond, right? I have to break a carbon-oxygen bond. And then I have to break a oxygen-hydrogen bond. And then, okay, I need a different color, purple. How many carbon-hydrogen bonds do I need to break? I'm breaking it all. So how many carbon-hydrogen bonds do I break? 5. Yes, so I'm gonna, whatever value that is, 5 carbon hydrogens. Did I break everything on my reactant side? No, I still have to break oxygen. So I just break 1 oxygen double bond, right? No, you gotta break 3 of them because there's 3 in the balanced chemical equation. There's 3 of them there, even though I just drew 1. And yes, if there's a bond enthalpy question like this, we do give you the structures. We're not at the point you know that oxygen is a double bond. So it will be shown just like this. So we also break oxygen double bond, 3 of them. So do make sure that you're breaking a double bond, not a single bond. The structure does show it has a double bond. Okay, so all of the energies are down here. So we just add all of those up. So we have carbon-carbon, so 348. We add it to carbon-oxygen, so 350. Oh my gosh, is my pen dead? I'd be really mad. My pen dead? Yes, it is dead. Okay, perfect. Perfect. All right, so carbon-oxygen is 358. Oxygen, hydrogen is 463. Then we have 5 carbon hydrogens, so 413. And then 3 oxygen oxygens is 495. Do make sure that you are looking at the right one. So here we have a double bond, there's a single bond. So do make sure you're using the right one. You add those up, they equal something. Okay. So all of that process of breaking is endothermic. It requires energy to do that. Okay, let's look at the other side and look at, okay, what are the things I have to make? Making bonds are always exothermic. They always release energy, but we still do it the same way. Look and see what are all the bonds I have to make. So it looks like here, I need to break this carbon-oxygen bond, carbon-oxygen double bond. But think very carefully on the total product side of the reaction, how many carbon-oxygen double bonds do I break here? There are total of 4. Yes, there are 4. Because there's 2 carbon oxygens in a CO2, but then there's 2 CO2, so there's 4 of them. All right, how many oxygen-hydrogen bonds do I make? 6, yes, again, because oxygen, hydrogen there's 2 of them in a water, and then there's 3 of them. And so we do the same thing. So 4 CO double bonds, so that's 799. And then 6 oxygen hydrogens, that's 463. All right, now we add everything up. So to break everything, this is how much money I need. I need 4,719 kilojoules of energy to break everything. But then once I reform them, I get this energy back. So I actually form 5,900, you okay? Okay, that sounds like an emergency alarm. Hopefully it's not an emergency yet. Okay, 5,974 kilojoules is what we get back. Okay. So, just based upon this reaction, can you tell me, can you predict the sign of enthalpy of this reaction? Minus. Why is it delta H negative? It's combustion. It's a combustion reaction, right? Burning things, we love it, right? Because reactions release energy. So this is a negative enthalpy of reaction because, all right, and this is the concept that the bonds that we make are stronger than the bonds that we broke, right? Because if we put these values into my makeshift equation, delta H equals break minus make, we see that the delta H of this overall reaction is equal to 4,719 kilojoules minus all the bonds we made. So 5,974 kilojoules, and we see, yes, delta H is in fact a negative number to go along with that, right? So do recognize that this last way that we calculate delta H, we break the reactants, but we make the products. So don't think that this is delta H equals reactants minus products. I don't want you to think that, because when we do like formations and stuff, when we, like for example, this question, where I give you delta H as a formation and I ask you what is the overall enthalpy of this reaction, you always do products minus reactants. That's a different equation when you use formation values. It's products minus reactants. But in bond enthalpy questions, it's the bonds you break because it's endothermic minus the bonds you make because it's minus because it's an exothermic process. But yes, technically it is, you're breaking the reactants and making the products, but I don't want you to think it's reactants minus products. That's not right. It's break minus make. Okay. All right. So that's the last way you do delta H. I like this way. I like breaking stuff. So, okay. All right. We have 15 minutes. So let's go over chapter 16. Yeah, let's do 20. Let's do 20. Okay, so we have a monochromatic light source. It delivers that much energy per mole of photon. What is the wavelength of light in nanometers? Okay, so there's a bunch of stuff going on here. So we have an equation that tells us based upon the wavelength or the frequency of light, each of those photons has a certain amount of energy. So either h nu, so this is frequency, or hc over lambda, right? The energy of a photon is proportional to its frequency, or it's inversely proportional to its wavelength. right? It's the second one that's going to be more important here because this question is asking for wavelength. So this is the equation that we'll use. All right, so the energy of a photon is related to its wavelength. But let's look at the information that's given. Did I give you the energy of a photon? No, I gave you the energy of a lot of photons, right? I'm giving you the energy of a mole's worth of photons. So what a lot of students will do is they'll just try to shove that number into this equation. Because we give you this equation. And so you'll try to shove 227 in there, but that's not the number you want to put in. We need to scale this down to, okay, this is how much a mole's worth of light has. How much does one photon of light have? All right, so that's the idea here. So a couple ways we can do this. So I like to rewrite this as, okay, 2,270 kilojoules is in 1 mole of photons. So we need to get this into a unit of just energy per 1 photon. All right, so let's change the unit in the denominator first. 1 mole of photons is equal to how many photons? 6.022 times 10 to the 23. Yep. Great. Now I have it in an amount that's per 1 photon, but I need to go one step further. This is in kilojoules. You probably want this to be in joules. 1 kilojoule is 1,000 joules, and the reason is because Planck's constant is in the unit of joule second. So before we plug this in, we need to make sure that energy is in joules. All right. So we divide by Avogadro's number. So now we get that just one singular photon has 3.77 times 10 to the 19 joules worth of energy. That's 1 photon. This is the number that goes into the equation. That's the number, not 277. But you know 50% of students will just try to shove 277 in there, all right? And then at that point, it's just plug and chug. Planck's constant, is that something you have to memorize? Never, no, it's in the packet somewhere. So I'll just set it up. 6.626 times 10 to the negative 34 joule second, that's Planck's constant, times the speed of light. Do you have to memorize that? Probably not, no, it's in the packet. So 3 times 10 to the 8th meters per second. But if you do a lot of practice problems, I promise you'll just memorize it. All right, divided by wavelength, and that's what we're solving for, equals that 3.77 number we just got, joules. All right, because remember, this equation, whether it be Planck's constant times nu or Planck's constant speed of light over wavelength, both of those tell you the energy of 1 photon, 1 photon. Okay, and then you just solve for this, solve for wavelength. So just take all of this stuff in the numerator and then divide by that joule number. You get that the wavelength, sorry, I'm being messy. Wavelength equals 5.27 times 10 to the negative 7 meters. All right, so that's the wavelength, but that number is real ugly. Okay, so it's probably better to convert it into a value that looks nicer, and that's why this question asks you to show it in nanometers. I'll remember these prefixes coming back. So nano means how many? Like to the 9, yeah, so 1 meter has 1 times 10 to the 9 nanometers in it. So this ends up being 529 nanometers. See, doesn't that number look a lot nicer? Yeah, okay. That is green light. That's green light. Okay. All right, so there's a lot, I love questions like these, okay? There's a lot, there's always a question on chapter 6, there's always a question utilizing this equation, whether we ask for energy of a photon, frequency or wavelength, and then relating it to a mole amount. All right, usually that question always comes up. So do understand how to navigate these questions or these equations and relate it to a mole amount if necessary. Because if I just ask, you know, like, what is the energy of a photon with this wavelength? Then yeah, you just plug and chug this equation if I just want 1 photon. But if I want a mole's worth of photons, we got to bring in Avogadro's number. Okay, let's look at this question because students like to neglect this. Okay, to be real scientists, we need to understand just relative energies of the different parts of the electromagnetic spectrum. We can only see visible light. Visible light is just a tiny, tiny sliver of the electromagnetic spectrum, but there's lots of E&M radiation out there outside the visible spectrum, and we should know their relative energies. But just before we get into that, let's relate energy, frequency, and wavelength, all right, of a photon. And it actually comes from this equation up here. Okay, if energy of a photon increases, how does its frequency change? It also increases, yeah. So high frequencies mean high energy. But how does wavelength change? Decreases, yes. So that means short wavelengths have large frequencies, also have large energy. So that is the relationship. This really isn't something you have to memorize. It actually just comes from these equations up here, right? Okay. Because that's useful. So like exam questions, so what I like to do is think about relative on the electromagnetic spectrum, what's high energy, what's low energy, and then what comes from that is frequencies and wavelengths, as long as you know the energies. So, okay, select all the regions of the spectrums that have higher frequencies than green light. So this green light, that's in the visible region, right? Right? So let's just draw like a relative scale. There's our visible light. Okay, so like a rainbow is Roy G. Biv. Let's do low energy over here. And then we'll do high energy over here. Okay, so in our rainbow, Roy G. Biv, what has low energy? Red, yes, red is our lowest of energy. So I'll write it in red over here, red. Okay, and that means violet is higher in energy. Yes, violet. Let's do purple, violet. And that means green is in the middle, right? So that's our reference point. We want, what do we want? We want, what are the regions of the spectrum that are higher frequencies than green light? So if I'm asking you higher frequency, I'm actually asking you higher energy, yes. So see how all of this is related, higher energy. Don't memorize more than like one thing. Okay, so since I say higher frequency, I also mean higher energy, or I could have said shorter wavelength, right? I could say shorter wavelength and the question remains the same. Okay, so let's look at these. Radio waves, where do those show up? On the right or left of this visible spectrum? Yeah, on the right. So red, radio waves are over here in the low energy region. Infrared is next to what color? Red, yep, so infrared is right there, okay? We're not that creative. On the other hand, UV light, which stands for ultraviolet light, is on the other side of what color? Violet, yep, so UV light is over here on the high energy side of our visible spectrum, all right? Red light is right there. Microwaves go where? Between IR and radio, yeah. Okay, and then X-rays are really high energy, yeah. X-rays are really high energy, okay? So, yeah, I like to just reference myself to the visible region. I know that it's sandwiched between UV and infrared. I know radio is the lowest and X-ray is the highest of energies there. Okay, so let's answer the question. Which ones have higher frequencies than green light? It would be violet, UV, and X-ray. Right? And so how I approached this was I understood higher frequency means higher energy. Okay, so let's do this one. All right, so this is related to our Bohr model of our atom. Okay, Bohr model of our hydrogen atom. So this question is fairly straightforward. This question, if you're good at it, it'll take you 30 seconds to do. I want you to do this question and not the coffee cup calorimetry question. Right? This question, I'm asking you, select the electronic absorption of an electron that results in the absorption of a photon with the shortest wavelength. All right, so if we think about our Bohr model, all right, we have like an electron, right? All right, so electrons only interact with light when they move between energy levels. When an electron's just hanging out on a energy level, it's not radiating any light. Light is only involved when there's movement. So let's think about it. In order to push this electron up to a higher energy level, that should say 3. In order to push this electron to a higher energy level, do we have to put energy into the system or take away energy from the system? Does the system gain energy or lose energy in order to promote an electron higher, to make it jump? It gains energy. So remember, light, a photon is energy. So does an atom absorb light or emit light when an electron jumps up? It absorbs. So the idea here is an electron will be promoted if light is absorbed, because light is energy, right? Energy will make the electron jump. But when an electron falls back down, that same energy is actually emitted instead, right? So when the electron jumps, light is absorbed. When the electron falls, light is emitted. So based upon this question, what are we looking for? Are we looking for a jump or a fall? We're looking for a jump because they say absorption. So that means we can eliminate half of these options, right? So we have 5 to 1. Is that, so energy level 5 to 1, is light absorbed or emitted there? Emitted. Okay, 5 to 4, emitted. 4 to 5. That one's absorbed because it's jumping, right? That one's absorbed. 1 to 5. That one's also absorbed. 6 to 5, emitted. So we eliminated over half of them. So we just need to look at C and D. C and D. All right? So this is where the other part of the question comes into play. We identified what transitions absorb energy, but now we need to figure out which transition results in the shortest wavelength of light. So go back to our relationship up here. Short wavelength means what energy? High energy. So we are looking, overall, we are looking for a large jump. Large jump. So which answer is it? C or D? Which is our largest jump? D, yes. Okay, actually, let me just change this. Let me change this. What if I said, so 4 to 5, what if I said 4 to 5 or 2 to 3? How does the answer change? So we're still looking for the largest jump, but it's a little bit trickier here. So let me draw a better energy level diagram. All right, actually I'm going to do 2 to 3 and 3 to 4. All right, so those are my two options. Which one of these, 3 to 4 or 2 to 3, has the higher energy jump? Which one? 2 to 3. But some folks out in the audience might be thinking, oh, but they both just go up 1. So the idea with the Bohr model is I did not put the energy levels equally spaced, because if I did make them equally spaced, n equals 1, 2, 3, 4, if we compare 3 to 4 and 2 to 3, don't they look like the same jump? They look like the same energy, but is this an appropriately spaced Bohr model? No, it's not. The idea, the detail with the Bohr model is that the energy levels get closer and closer together. And that's the only way we can answer that question, is if we draw them appropriately spaced. So we see that 2 to 3 is in fact a larger jump than 3 to 4. So the answer would be 2 to 3. Okay, and that's how we would make the question a lot harder, because the original question wasn't as hard. All right, so best of luck, everybody. Okay, refer to the key for the questions that we did not finish.